Welcome to Chapter 2, Part 4. This is going to be our introduction to resonance. I would say for this first chapter that we are covering, this is the skill that most students will probably need the most practice with. I have up an additional resonance practice up on eCampus. A lot of your homework for this chapter will have resonance practice. And if you find that you need more, please let me know. I will also be including this week some extra videos of me working through some resonance problems if you need some extra help. And also, as always, please come into office hours. We can do this stuff together in that Zoom environment. Okay, so resonance is something that we're often introduced to in general chemistry, but we often need a little bit of a refresh. So when we talk about Lewis structures and bond line structures, right, we are talking about how atoms come together and share electrons. But there is a limitation to Lewis structures. And we see that a lot in organic with different types of multiple bonding, like double and triple bonds, in charged molecules like anions and cations, and with our heteroatoms that usually have lone pairs. And so one easy example for us to start with is this allyl carbocation. Now, there are some words there. Let's talk about that. All right, we're looking at a 3-carbon chain. Right, there is a double bond here between the first and second carbon. And so we know that there are 2 hydrogens on the end because it's a neutral carbon with only 2 bonds. The carbon in the middle has 3 bonds and is neutral, so it has 1 hydrogen. And then the carbon on the end has a plus charge, so it must only have 3 bonds. Remember, those common bonding patterns are important to know. Now, in this scenario, this is a valid Lewis structure, but there is another valid Lewis structure that could be drawn that shifts only the double bond and the charge. Now, why do I say this is a limitation in the Lewis structure? Because all of the atoms are in the same place. We still have 3 carbons in a row. We still have a CH2 on one end, a CH in the middle, and a CH2 on the other end, right? The only difference is in the location of a pair of electrons. And that is how we describe resonance. It is the ability to draw 2 different valid Lewis structures for the same molecule. And so both of these structures are valid and represent the same molecule. 3 carbons in a row, 2 hydrogens on either end, and 1 hydrogen in the middle. And what we learn when we study molecules like this is that neither one of these structures is perfect by itself, but in reality, it's a hybrid of the 2. And so you'll hear that word periodically, a resonance hybrid. All right, so, and you can see that here, it's inadequately described by bond line structure. Neither one of these 2 structures is exactly right. Now, how do we know that? Well, for instance, a single bond, right, is longer than a double bond. And so if this structure was accurate, you would expect to have a short bond and a long bond. But in reality, both bonds are the same length, which can be measured. And what's interesting is they're somewhere between a single bond and a double bond. So we say that this pi bond is delocalized. It's not just between carbon 1 and carbon 2 or 2 and 3. It's more spread out than that. It really is something more like this, where they're both 1.5 bonds. And the plus charge, right, is spread out between the two end carbons. And so the reality of the molecule is understood best if we know all of the resonance structures. For instance, reactivity might happen at a positive carbon. Well, in this case, you have two partially positive carbons. And so resonance can be really important in understanding behavior. It can also be important in stabilizing, right? If charge is less stable, right? So a charged ion is less stable than neutral. Being able to spread out the charge is stabilizing, right? So delocalizing, right? Or spreading out of a charge can be stabilizing, right? So we're going to talk about resonance in reactivity. We're also going to talk about it when we talk about stability. And we talk a lot about stability in this course. Now, how does this work when we think about bonding? Well, when we look at these 3 carbons, right? And so we'll have our picture up here. These 3 carbons are held together by sigma bonds, right? That's that head-to-head overlap of some sp3 or sp2 orbitals, sp2 in this case. And a pi bond, right, so for our double bond is going to be the overlap of 2 p orbitals. Well, this carbon that has a plus charge would also have an empty p orbital, and it's close enough to where it can also overlap. So those 2 pi electrons are shared over the whole molecule instead of just between 2 carbons. It's able to spread out. Those electrons are able to spread out more, right? Again, why we use the term delocalized. So if, for instance, we had the neutral molecule, right? That was a carbon with the double bond, and then this carbon had 3 hydrogens. Well, if that carbon on the end has 3 hydrogens, then the lone pair in the double bond can't spread out. We would call that particular bonding pair, that double bond, localized. It's only between carbon 1 and 2 and not spread out. And so that's a little bit about that vocabulary. Now, we talk about molecular orbital theory a little bit in organic, but for the most part, we cover it in organic, or we use it in organic too, when we talk about dienes and aromaticity. When we get there in organic too, I will give a refresher on molecular orbital theory. I don't think it's crucial for us to think about molecular orbitals right now. So you're going to notice that I'm just going to fly through a couple of slides here. All right, now when we're talking about this delocalized pair of electrons, when we're talking about multiple Lewis structures that tell the story of our molecule or our ion, how do we represent this? Because there is a grammar to chemistry, right? There are symbols. We have to know how to use them. And something that is very important for you to understand is the resonance arrow. So when we talk about resonance structures, we use a resonance arrow. This is different from an equilibrium arrow. An equilibrium, there we go, arrow is forward in one direction and backwards in the other. It's 2 arrows, and they can be either half a barb or they can be double barbed. It doesn't really matter. This is dynamic. This one is more like an average, right? Equilibrium, you are going in both directions. You are going back and forth. But resonance, this is a hybrid. That would be like saying, let's see, there's so many examples we use over the years. A mule. A mule is a hybrid of a donkey and a horse. The mule doesn't go back and forth, right? It's not a horse on Monday and a donkey on Tuesday. It is always a mixture of the two. It is always a hybrid of the two. That is what this arrow right here indicates, right? And so it's important that you recognize the difference. It is not going back and forth. It is an average of the different structures. So again, so like this lone pair here, or not lone pair, this double bond, the pi bond, it isn't going back and forth, right? Neither one of these two structures is correct by itself. It's something in the middle, right? It's a mule. If this, is a horse and a donkey, it's neither one of them. It's something, it's a combination of the two. Then you're frequently going to see brackets around all of your resonance structures. Sometimes there's 2, 3, 4. Sometimes there's many. And to indicate that you have a group of resonance structures and you're not moving through the steps of a reaction, you'll put brackets around it. Let's see, what analogy did this book use? Instead of the mule and the horse and donkey, you can also, if you would prefer, to think of this in terms of fruit. A nectarine is formed when you, I don't know how plant breeding works, but when you mix together a peach and a plum, you get a nectarine. And so the nectarine is always a mixture of the two. It's always a hybrid of the two. It's not ever a peach or a plum. It's always something in the middle. That's kind of what we think about with this resonance hybrid. Now, this is a very simple example. Resonance hybrids with dotted lines aren't always possible to be drawn, but it does help you to visualize, right? It's never a full plus charge on one carbon and a full double bond. It's always some mixture where you get partial positives and you get something between a single and a double bond. And as we mentioned earlier, and it bears repeating, resonance stabilizes molecules. Anytime you have a lot of extra charge, a buildup of negative or positive charge, that's going to be destabilizing. And so if you can spread that charge out, you can spread the electrons out more, that is going to have a stabilizing effect. All right, now this is a very important topic, the curved arrow. When we use it in chapter 2, it is simply a tool to get from one resonance structure to the next. So in the example we've been using, to get from one example to the next, we can use a curved arrow. And what is very important, and we're very nitpicky in chemistry, details are very important. The tail of the arrow, where the arrow starts, is always where the electron is currently located. Arrows start where the electrons are, and they end where the electron is going. All right, so in this example, it's the pair that is shown in the pi bond moving to form a double bond on the other side. So we start the arrow on the double bond and we point towards the single bond, right? Because we are going to form the double bond over here, right? It's always where the electrons are to where they are going. Now for resonance, again, it's important to recognize it's not going back and forth. It's not showing actual bonds breaking or forming. It's just a tool to help you get from one resonance structure to the other. And why is this important? Well, in the next video, I'm going to show you common bonding, or not common bonding patterns, we already did that. Common resonance curved arrow patterns. And so if you get stuck on a resonance problem, having these 5 patterns to fall back on can be really helpful. All right. Another thing that's important about the arrow is a double barbed arrow, shows 2 electrons moving. And in some, especially when we get to chapter 10 and talk about radicals, a single barbed arrow represents 1 electron. Now, this will be important mostly in your lab reports where you actually draw things for me. And then in your homework, if you're asked to put arrows in place, you're going to have the option of a double barbed or a single barbed arrow. And it's important. One communicates 2 electrons, the other communicates 1 electron. So you have to know what you're doing, right? You have to be detail-oriented here. Now, before we end this video, let's talk about some rules. When we are talking about resonance, right? Let's see, rules. What am I doing? 1, you cannot break single bonds. If you break a single bond, then you are changing the order in which the atoms are arranged. And if you do that, that is a chemical reaction. That is not resonance. That is not 2 valid Lewis structures of the same molecule. That's 2 different molecules. So do not break single bonds. It says sigma bonds. Single bonds are sigma bonds. The only bonds that are quote unquote quote breaking when you are doing resonance are pi bonds. So it's always double and triple bonds and lone pairs that you're moving around. So do not break single bonds. Again, they break in a chemical reaction, not for resonance. We will break lots of single bonds later on when we talk about reactions. We are not going to exceed the octet rule. This is just a good rule to remember. Don't exceed octet for second row elements. One of the most common notes that I write on papers is carbon cannot have 5 bonds. And so you will see that from me. You will hear that from me in videos. It's why it is so important that you understand bond line structure. And when you are getting started, it is helpful for you to go in and say, maybe I'll use a different color. Okay, let me draw in all my little hydrogens. Because if you're trying to move electrons around, you got to be real careful not to put a 10th pair on oxygen, nitrogen, or carbon, right? Carbon might have less than an octet, but it will never have more. This is just that note. Carbon sometimes has less than an octet. Formal charge is super important. And we're going to make this like it's a rule here, even though they don't call it a rule. Let's say number 3. Formal charge overall is maintained. So every resonance structure that you draw should have the same overall charge. So you noticed here, this is overall +1, this is overall +1, right? They have either, 2 of the carbons are neutral, 1 has a +1. 2 of the carbons are neutral, the other one's a +1. They won't always have exactly the same number of formal charges, but the overall formal charge should be maintained. So for instance, in this example here on the left, every atom in there is neutral, right? The oxygen has no formal charge. It's 2 bonds, 2 lone pairs. All of the carbons are neutral. So you can draw a resonance structure, and I'll draw what they're showing here. We'll go over these patterns in the next video. But what they are showing, so let's think about that. They're showing one of the lone pairs on the oxygen moving down, and then one of the bonding pairs in the double bond moving out. All right, so this carbon right here had 1 hydrogen, and then double bond and single bonds to carbon. Now it still has 1 hydrogen and then 2 single bonds, and so it's 3 bonds and a lone pair. It's going to have a negative charge. The oxygen has three bonding pairs in a lone pair. It has a positive charge. So do you see overall it's still neutral? So overall, this is neutral. Overall, the resonance structure is neutral. You're never going to have a resonance structure that is a cation and then one that is an anion, or one that has a +1 charge and another one that has a +2. They're always going to be overall the same, right? Because resonance isn't breaking bonds. You're not going to lose or gain electrons. You're going to have the same number of electrons. It's just they're located in different places. Right here, it's maybe shared a little bit more evenly. And then in the other resonance structure, you see the carbon has a little bit more of that density. And you can see that example on this next slide. And that is valid. Now, they're not equal. We will talk in another video about major and minor resonance contributors. Not all resonance structures are created equal, but they will have the same overall formal charge. All right, in part 5, in the next video, we will talk about pattern recognition.